Okay, good morning everyone. Welcome to the second week of the program on Discrete Integrable Systems. I'm Arvind Ayyer. I'll be the chair for the morning session. So for those who were not here last week, I remind you to ask your questions using the mics on the table. So if you have a question, please raise your hands and we will pass around the mic to you so that the questions are also available on the live stream and the recording. Okay, so the first talk of the session is by Deepak Dhar from ICTS, and he'll talk about phase transitions in a system of long hard rods on a lattice. Please, Deepak.
Okay, good morning everyone. So I'm happy to have this opportunity to give some description of my work. But I have a little bit of a misgiving about the title or the subject. The talk does not fully fall in the subject areas described in the conference title. So, I thought about what I should discuss, and I still decided that I will talk about this. So the work I'm discussing, it's a lattice model, so discrete part is okay. And it's a variation of the dimer model, which is a very classical model of integrable model in statistical physics. And then the starting point of my own work in this model, as you will see, starts with this difference equation. FL is equal to FL minus 1 plus FL minus K. So difference equation is also there. And finally, we will conjecture some asymptotically exact results for lattice models in d dimensions, and which suggests that the model may be partly soluble in some suitable limit. So it's not really integrable, but maybe there's some limit it becomes integrable or some such thing. And you will have to decide whether it becomes integrable or not, because our work is more like a conjecture. But I still thought it will be interesting and you will find it interesting. So let me just go ahead. Okay, so this work is done with a student, BSMS student, Agam Shah, and R. Rajesh in IISc. And some parts of it have been published earlier. Okay, so this is the plan of the talk. I will start by the general discussion of what are geometrical phase transitions, and then I will get to this phase transitions in system of long needles. So that is, we call needles of length k, we call them k-mers, because dimers are length 2 and trimers, and this is k-mers with length k. And so this model undergoes more than one phase transition. There is a low density disordered phase. At low density, if you take very low density of these rods, things at different large distances are roughly uncorrelated. If this rod is up in various orientations on the lattice, the next rod can be in other ways. So there is no orientational order. But if you increase the density, it goes into a nematic phase where the rods become more or less aligned in the same direction. So that is called the nematic phase. And if you go to even higher density, the nematic phase goes into some other phase. So we will discuss these phase transitions. And we start by discussing the entropy of k-mers at full packing. If you take these k-mers on a lattice, let us take this ZD, d-dimensional hypercubical lattice, then how many ways can you pack it fully? That is, we try to get an estimate for this entropy. And then there is a nematic phase transition. There is a phase transition from the nematic phase to high density disordered phase. I will discuss this and then summarize. Okay, so let us discuss geometrical phase transitions in general. So the point about geometrical phase transitions is that these are conceptually similar, and one doesn't need to invoke notions of energy and temperature and stuff like that, which are rather complicated. And you only work with notions of probability and geometry. And by geometry is only meant the high school geometry with, okay. So this work has long history, starting with the work of Onsager. Onsager in 1949 had discussed the case of long spherocylinder rods in a solution, and he showed that if the density of these spherocylinders have only hardcore interactions between them, no other, and they are just in solution at low density, then what happens is that if you increase the density of these spherocylinders, there is a phase transition in which they become parallel to each other. So the limit of, he couldn't solve this model in general, but he solved it in the limit of infinitely long, infinitely thin spherocylinders. So my work is sort of related to that. We are studying the Kmer model, but in the limit of large K, where K is much bigger than 1. And this model, Onsager showed there is a phase transition in this model in the large K limit, and he actually got the exact asymptotic free energy in this limit. And the Lattice model was studied by Swansea in 1963. And there is some substantial time lag between these two. But I will not discuss the rest, but I'm mentioning that there are other geometrical phase transitions. If you take hard spheres as a function of density, at low density it's a disordered phase. At high density it becomes crystalline with periodic order. And the other geometrical phase transition which is well studied is the percolation model. Okay. So phase transitions in hard interacting particles, one can study assemblies of hard objects of other shapes, triangles, squares, hexagon, octahedra, cubes, long rods, rectangles. These are the ones we will study. But all these others have been studied as well. And they are of interest and they show slightly different behaviors. The structure of the dense packed state depends on the shape, and so does the nature of the transition between these states. And so we will consider molecules can only lie on a grid. So these are the lattice models. Onsager studied the continuum model. Okay. So these just pictures of some lattice models. These are 2 by 2 squares. And as you increase the density, the typical configurations change. These are long rods, 4 by 1. And again, you can see there is some change in behavior. And these are called Z-shaped molecules, and these are L-shaped molecules, and these are T-shaped molecules. So these are all tetramers, tetraminos, 4 sides. Each particle occupies 4 cells, and you can get interesting behavior. I will not study all of these, but I just like these pictures because they show the rich geometrical structures which are possible in these simple models. Okay, and it's also important to realize that these systems are not just for theoretical interest. You can actually experimentally realize these rather easily. So Onsager himself suggested that if you want to study long rods, it's hard to find very long linear rod-like molecules, but tobacco mosaic virus acts like a big hard particle, and they are roughly of same size. So you can study tobacco mosaic virus in a solution, and it undergoes a phase separation. So at some temperature, there is not much effect, but if you change the density, then this is in ordinary light, you don't see much difference. But if you see polarized light, then the phase in which the molecules are aligned rotates the light differently in different directions, and you see all these colors. And so this is a very macroscopic realization, which is rather easy to set up experimentally. Okay. Okay.
Sorry, could you go back? I didn't understand the figure completely. So the left side is the...
It's the same stuff in ordinary light. You don't see much difference. There is phase separation. This phase has higher density of virus particles than this, but you don't see much difference.
I see. And the black one is pure fluid.
This is with in the polarized light, and you put crossed polarized,
Yes,
then
yeah.
this shows black color and this doesn't show black color.
Okay.
Okay.
Thanks.
And different shades are because of the shape of the test tube and other complications. Okay. Okay, so we will study lattice models of long rods. The picture is for a square lattice, long straight rods of length k, width 1, and only hardcore interactions. So I will take the pictures where the rods are sort of rectangles of width 1 and length k. You can take rods which occupy sides of the lattice, but we are taking rods which occupy squares of the lattice. And all allowed configurations with a given number of rods are equally likely. That is the whole definition. You take some lattice, put in a fixed number of rods, and what is the average behavior of such a configuration. Okay, so there is the earlier work. And the first thing to realize is that if you take these k-mers on a lattice, there is a finite entropy per site at close packing. If you try to pack them as closely as possible, then you can break the whole big lattice into k by k squares. Each square can be packed in 2 ways. And so the total number of configurations is greater than equal to 2 to the power n by k squared. This is the number of k by k cells, and each cell has 2. So the number of configurations is greater than this, and this increases exponentially with n, which is the size of the lattice, number of sites in the lattice. And of course, these are very simple structures. Much more complicated tilings are possible in this system. And so this number is very different. Okay, so the question which was asked was, is there an ordering transition as a function of density in the lattice model? Because this was proposed as a lattice version of the model which was studied by Onsager. And in the Onsager model, there is a phase transition. And so does the lattice model also have a phase transition. And this was actually not so easy because it was an unsolved problem for a longish while. And in 1975, there was some review article Dijen and Pro wrote, and they said that it is not clear that there is any transition in this model for any k. Well, it is known that k equal to 2, there is no phase transition. That is the Dimer model, and in Dimer models, Heilmann and Lieb had shown that there is no phase transition possible. People they couldn't prove this rigorously, but they studied this problem using Monte Carlo simulations and transfer matrices. And it seems like in k equal to 3 or 4 also there is no phase transition. Okay, and it was very clear that there is no orientational ordering at close packing. If you take all close pack configurations with density 1, that is the maximum possible density, at that density there is no orientational ordering. So then why should there be any orientational ordering in between? That was the sort of plausibility argument. And that was the reason for saying that it's not clear that there is a phase transition for any k. But actually we found by Monte Carlo simulation that if you take k bigger than 6, then in the system in 2 dimensions, there are actually 2 phase transitions. This is the low density phase. This is not very, very low density, 0.66 fraction of all the squares are covered. But there are equal number of horizontal and vertical rods in this system. But when you increase the density to something like 0.89, then the typical configuration looks like this one, where almost everything is parallel, very high amount of order. But if you increase the density to even bigger, then the structure goes to something like this, which actually has equal number of horizontal and vertical rods. And these simulations are not very easy to do because there is jamming problems, and it takes time to equalize and so on. But we were quite confident that these things have thermalized, and at this density, this is a typical configuration. And so it actually shows 2 phase transitions. This is called disordered phase, this is called nematic phase, and we call this the high density disordered phase. So the nematic order parameter is not a monotonic function of density. First, from here to here it increases, and then it goes back to 0 again. Okay. So firstly, let me discuss this first transition from here to here. Here, there are these disordered horizontal and vertical rods are both possible. Here, there are two possible ordered states. They could be all horizontal or all vertical, and or mostly horizontal, mostly vertical. And so it looks like the Ising model. If you coarse grain this system, then on large scale, it will look like either this kind of state is possible or that kind. So there are, so there are two ordered states, and it is the phase transition is in the universality class of Q equal to 2 parts model, which is called the Ising model. So on coarse graining, you would expect this model to be in the Ising universality class. And this seems to be consistent with what is known numerically from simulations also. And if you can take this model defined on a triangular lattice, then each rod has 3 orientations, then it goes into the Q equal to 3 parts model. It's different. Okay, and this is consistent with the results. So just this comment, at intermediate densities, the ordered state has higher entropy than the disordered state, which sounds contradictory at first. How can the ordered state have higher entropy than the disordered state? But basically, there are two components to the entropy. One is the orientational entropy, one is the translational entropy. If you have the state which is this one, it has low orientational entropy, everything is parallel. But because they are parallel, they can move around much more freely. And so it has higher translational entropy. And the system only cares about the sum of these two, so it maximizes the total entropy, which comes in this case where translational entropy wins over the orientational entropy. Okay, so now let me discuss the entropy of long rods at full packing. So suppose, if we take a L by L system and try to cover it with chimeras, sometimes you may not be able to cover everything. So that's a minor nuisance. So we will take the L to be multiple of K, then you can cover them fully. So it's take KL by KL lattice and say how many ways can I cover it? And the answer is that it varies like the volume multiplied by a number, and that number we call S. This is the entropy per site of the packing. So S is log of the number of ways divided by K squared L squared, and it's the we call entropy per site. So the exact value of entropy is known for S of 2. That was the work of Fisher and Castellin, and it's known to be this Catalan constant divided by pi.
So you presented many numerical simulations. So can I ask how, for example, in the D equal 3, in the K equal 3, K equal 4 cases, those simulations, Monte Carlo simulations?
They don't show any ordering. So it just looks disordered at all densities.
No, he's asking how you do the simulation.
The details of simulation. So we use various algorithms. The most effective one is called deposition evaporation method. So you put some configuration, you evaporate a K-mer with a probability, and you try to put it down with some probability with the detail balance satisfied. And this algorithm is proved to be ergodic. I don't know what is the time scale for ergodicity, but in principle it is ergodic. And we have tried to ensure that for our simulations it works. If you go to very, very high densities, then it is harder. Okay, so first let me obtain. So this result we will obtain using lower and upper bounds on Sk in 2D. So let me first obtain the lower bound on Sk. We have already shown that Sk is bigger than equal to log 2 by K squared, because I brought in K by K small squares, each one had log 2. But you can do better by this. Take this big lattice KL by KL, break it into stripes of length K, KL and width K. So they are made of long stripes like this. Each stripe you can cover with K-mers, roughly like this, in many ways. And then the entropy can be obtained by estimating the entropy of covering a single stripe. So this is omega KL is the entropy of a single stripe of length KL, raise it to power L because there are L such stripes, and that is WL, bigger than equal to. But this omega satisfies this recursion relation, because if you take something of length K, the first one could be a vertical, then it is the rest is omega r minus 1, or if it is not vertical, you have to put K horizontal stripes to cover it fully, and so it is omega r minus K. Okay, and so this recursion equation, of course, is easy to solve, and it goes like lambda to the power r, and lambda satisfies this equation, and this translates into a lower bound of S of K. S of K is bigger than equal to log lambda by K. This denominator comes because this is lambda is the eigenvalue for the transfer for the system for one column, but one column has K sides, so you have to divide by K. Okay, so if I solve this equation and I write lambda is equal to 1 plus b by K plus order 1 by K squared, then you can see that B satisfies this equation B exponential B equal to K. This is called the Lambert equation, and it has an interesting complicated solution. B of K is log K by, firstly it looks like log K, but then there is a correction term which is log K. Then you write that correction term. Then the next correction term is log K, and the next one is log, 4 logs like that. And it's very complicated. Okay, but you should just, if you say that take the solution of this equation, then the correction is order 1 by K squared. So that is the systematics in terms of K. If you try to do perturbation theory in large K, you have to be careful. If you do it wrongly, then you will get log K, log K, and those kinds of corrections. Okay, so anyway, so this gives you that SKK squared divided by log K is bigger than equal to 1. Okay, upper bound on WL was obtained by Gagunashvili and Priejev in 1979. And they said that take this KL by KL lattice and let me take a subset of vertices of this which are at distance K from each other, these purple ones. And they said that I look at one of these vertices and see how I can cover this with a rod. So it can be covered in 2 K ways, because you can cover it either horizontally or vertically, you can slide in K ways. So I will tell you, so I number the way I cover it 1 to 2K, and say this one is covered in this way, this one is covered in this way, and so on. You specify the covering of each of the purple squares. So that is 2K for each. Now the question was, if you specify the covering of each of the purple ones, can this covering be completed correctly? And the proof of Gagunashvili was that if you give an arbitrary assignment of covering of the purple vertices, the rest of the stuff can be covered in at most one way. Sometimes you cannot cover it at all. For example, if I say this one is covered horizontally with number 2K and this one is covered with 1, then they will collide and it's not possible. Okay, so the maximum possible covering is the number of ways you can assign this to K to the power L squared, and Sk is less than equal to this. And this also goes like log K by K squared. Previous one went like log K by K squared. So this is log K by K squared. The coefficient has to be 1. Okay. So now we can study the generalizations to higher dimensions. You can imagine rods in 3 dimensions. And so this is a picture from Geschwind. And the conjecture we would like to make is that this result holds, the A equal to 1 result holds for all dimensions D bigger than 1. And so let us work in D equal to 3. And so it is clear that entropy in 3 dimensions is bigger than entropy in 2 dimensions, because you can take each layer and cover it with rods. That will give you the entropy equal to the S of 2. And total number of ways is bigger than this. But if you see how much is the difference between the 3-dimensional entropy and the 2-dimensional entropy, S D equal to 3, S D equal to 2, there is a perturbation theory argument which says that the difference is only k to the power minus k. But k is going to be large. So this is going to be pretty small. And to order 1 by k square, it will be just log k by k square. Okay. In fact, you can go to higher orders and it will be still the same. Okay, so the leading behavior of large k is unaffected. And this argument is extendable to higher dimensions as well. But we will let us work with d equal to 3. Okay, so this is the perturbation theory for d equal to 3. And the argument we use is used by Bellman and Nigams in 1967. So they said that I want to do 3-dimensional stuff. I want to have rods which are vertical or in the plane. Let me assign a weight to the vertical rods which is z prime, which is different from weight assigned to the horizontal planes. And let me do this more general problem. Omega is z prime L. It is the number of ways of covering the full stuff with weight z and z prime. This problem is soluble if z prime is 0, because then you just cover each layer, because z prime is 0, there are no vertical rods. And so omega z prime is omega z0L, and then you write a perturbation theory in z prime. There will be a term which is independent of z prime, then some power, other powers. The lowest power which will show up will be kth power, because in each layer you cannot just create one hole. You have to remove a whole rod, you will create k holes. And so the lowest term will be z prime by z to the power k, and next term will be z prime by z to the power 2k, and so on. Okay, and okay, so I do this. Then I try to determine what is A1. A1 consists of the following configurations. There are k rods, all in the same k stripe, and you have to do something, but the simplest configuration is that suppose you covered them with layers, but there was one layer in which there was a rod, another was just on top, and just on top like this, k. Then you can take this k by k square, which is vertical, and flip them to make k vertical rods. And this is the leading contribution to the possible configurations which are counted here. Okay, so then there are other terms which you can also estimate, but this is the leading contribution. So how often can I do this? How often can I find there is a rod, another one on top, another one on top, up to k? And the answer is that the different layers are independent. So the probability that the second one will be just on top of this is 1 by 2k. And so it's 1 by 2k to the power k minus 1. Okay. So the contribution is 1 by k to the power k minus 1 by 2k to the power k minus 1. And then you can look at other corrections and you can again estimate them. Each of them term by term is 1 upon k to the power k minus 1. So it is hard to prove, or we have not proved, that this sum of all these terms is finite, but it seems plausible. And if you assume that the series converges, then you will say that this perturbation theory is well behaved, and the corrections are only 1 by k to the power k, and then the result follows. Okay, so now I want to discuss the second transition. Okay, so again, there are some plausible non-rigorous argument. There is a conjecture which says the nematic to high density transition is a first order transition. And this is the chemical potential mu, and this is the density of holes. Instead of density of particles, you look at the density of holes. And as you increase mu, for 5, 6 there is smooth curve, but later on it tends to be sort of a jump. This is the behavior which is what we expect, or this is what we will try to show. As you increase k, the transition occurs at a higher value of mu, and the size of jumps becomes smaller. Okay, and in this large K limit, we will conjecture these results. So here, let us say that epsilon 1 is the density of holes before the transition, and epsilon 2 is the density of holes after just after the transition, the lower end of this first order jump, and mu star is the value at which the transition occurs. So the first order transitions are specified by the density before, density after, and the point at which the jump occurs. Okay, so the epsilon 1, k squared by log k tends to 1. Mu star, which is the chemical potential, that varies as k log k, and the coefficient of that is also 1. And the density of the second one, epsilon 2 by epsilon 1, tends to 0 for large k. So this is what we would like to show. The values of these multiplicative constants in the leading behavior are independent of dimension, which is also somewhat surprising. Firstly, that they are these simple numbers, and then they are independent of dimension. Okay. So let S of epsilon be the entropy per site when the density of unfilled site is epsilon. This is the density of holes. So we have an obvious bound that S of epsilon is bigger than S nematic of epsilon. S nematic of epsilon is defined as the entropy in the case where it is fully nematically ordered, where all the rods are parallel to each other, fully. There are no rods in perpendicular orientation. So this bound is obviously trivial. But the calculation of S nematic of epsilon is easy because it's a one-dimensional problem. If all the rods are parallel, the problem becomes a one-dimensional problem. And it's easy to find how many ways can one place L into 1 minus epsilon by k kmers on a line of length L. So the density of holes is epsilon, and this is the formula. It's straightforward to derive. Okay. So our key observation is the observation that for large k, the difference between S of epsilon and S nematic of epsilon is small. It is again of order k to the power minus k. So this perturbation theory works even for this problem. And so this difference is small. Now I just want to show this claim that the difference is small. So working in the grand canonical ensemble for the fully nematic case, the grand canonical partition function per site satisfies this equation lambda to the power k minus lambda to the power k minus 1 equal to z. So now I am not working in the fully ordered, fully packed limit. I am allowing for holes. There is an activity z for each site. Lambda of z is the partition function per column. And so this is the equation, so I take a strip of length k. This will be the, just a line of length L, and the partition function lambda is the partition function per site. Then this is the equation. So now I consider again perturbation theory in zy, but now we are doing the perturbation in the presence of holes. So I will write omega zy equal to omega z0, and then I will write perturbation expansion in zy. Now the first order coefficient is no longer non-zero, it is non-zero. You can have k holes vertical, and you can just put a y mud there, and so the coefficient will be a1 times zy plus zy squared plus zy cubed, and we have to evaluate each of these coefficients, and it's easy to work out this first coefficient. It is just n epsilon to the power k. Epsilon was the density of holes, and now I am taking epsilon to the power k. So if epsilon is fixed and finite and k is increased, then this contribution can be made very small. Okay. So for fixed epsilon, large k, this tends to 0. However, if you take the limit k fixed and epsilon goes to 0, okay, then this term is epsilon to the power k, but they is multiplying zy, but zy has to be eventually put equal to z. And z itself goes like epsilon to the power minus k, and so this product is of order 1. So it is not becoming very small, a little bit tricky. And so the first contribution of this first order term is finite. But then you can do a slightly more stuff. You can look at what happens if there are two parallel rods vertical as a correction to the case where everything is horizontal. That's a perturbation. And you can check that the contribution of this kind of configurations with 2 or 3 parallel vertical rods is equal of the same order as with just one vertical rod. So it's becoming a problem because I could put 2 or 3 or 4, or I could put R of them, and the total answer will be the sum of all these terms. And then you sum up all the terms, the answer is 1 minus 1 by lambda, and it actually diverges as epsilon tends to 0 because lambda will tend to 1. So the perturbation theory is not working because as if in the opposite limit where I let epsilon go to 0 first. Okay, so this shows the instability of the fully nematic state to creation of islands of opposite orientation near the full packing limit. Because if you go near the full packing limit, then the nematic state is not stable. So it shows you that there is an infinite amplitude of perturbation. But anyway, I plotted this f, which is the sum of all these terms, as a function of epsilon, numerically evaluated, and for k equal to 7, 14, 21. And this is the y-axis f is some 10 to the power minus 25 here. But if you go to small epsilon, this is a straight line asymptotically. So it will keep on diverging, it will keep on becoming bigger, and this will also keep on becoming bigger, and so on. But if you stop the perturbation series at the point where the transition occurs, those are the points which are estimated to be around here, then the series is well convergent. You don't go to the epsilon goes to 0 limit because we are not going to be there. We are going to be only near the transition point where epsilon is finite, and then this contribution is actually very small. So here it says the perturbation theory gives an asymptotic series in powers of z prime that is formally divergent at epsilon equal to 0, but gives very small corrections when epsilon is small but finite, and in particular up to the end point of the stability of the nematic phase. Okay. So now we want to go beyond this particular limit. So this is the tangent construction. So while S nematic epsilon is a good approximation to S epsilon in a substantial range of epsilon, it must fail for small epsilon. At epsilon equal to 0, it must fail because S nematic of epsilon goes to 0 as epsilon goes to 0, because I know that on a line, if the density of holes is small, the entropy is also 0. But S of epsilon is bigger than 0. We just showed that it's log k by k squared, right? So if you take this S nematic epsilon, it looks like this blue curve, but S of 0 is finite. And this curve has to be convex. So if you take any point S and draw a tangent to this, it must intercept at a value bigger than S0 for a convex curve. And so in particular, if I start here and I take a tangent to this curve, then all these values here will be not allowed, because then the intercept cannot be here. So in the regime 0 less than, so this point is called epsilon 1. And in the regime 0 less than epsilon 1, it is better entropically for the system to phase separate into two parts, one with nematic order with hole density epsilon 1, and the other one with no holes. But that one also has a finite entropy. Okay? And the part with holes has even more entropy, but there is only a finite part. And there is a sum of these two phase separation. Okay? So this is the statement. For large k, S epsilon is well approximated by S nematic epsilon, supplemented by the knowledge of S0 in the convex envelope construction. So we say that the actual entropy differs from this very little in this part, only by k to the power minus k. And it differs from this in this part where it is very close to the straight line. Okay. So since estimatic epsilon is very good and S0 is very good, we can estimate epsilon 1 to reliable accuracy. And you can just check with a little bit of algebra that epsilon 1 is also log k by k squared. Okay, so it's pretty big, which is comfortable for me because I didn't want epsilon 1 to be very small, there was problem. Okay, and again you can take, since you know this epsilon 1, you can also calculate the slope at this point, and you can show that mu star over k log k tends to 1 as k goes to infinity in this approximation. So in this approximation, epsilon 2, the whole density in the dense phase at coexistence is 0, which cannot be true. Okay, but so we are working iteratively, and we are saying that the correction to this behavior is small, and now we will estimate the correction. How much is the correction? Okay, so now I would like to argue that the asymptotic results remain unchanged even when we work with true function S epsilon and not S nematic epsilon. The effect of holes can be taken into account partly by a more elaborate but still approximate calculation. So we have a sequence of approximation. S nematic is less than some other function which I can calculate, and then there is an improved function I can calculate. Each of these is calculable, and for each of these you can make this epsilon tangent construction, and at each level the asymptotic behavior is unchanged. So we haven't gone to many levels of this approximation, but the argument is that it will not change, it will remain the same. Okay, so now let me just describe quickly this the high density disordered phase 1 construction. So instead of taking the old construction, I take the following construction. I have 3 types of tiles. One tile looks like this, 1 by k, the other is k by k, the other is k plus 1 by k. And I put these in some arbitrary way along a line, and then I can fill up this. This is a stripe, and then a many possible stripes. So I only look at configurations which can be created in this way using these tiles. Okay, and so that is called the HDD1, and then I can calculate the entropy of this. Is easy to calculate, and then I can again do the tangent construction. So this is just calculating the partition function of HDD1. So there are weights of these tiles. X is the weight for each column, Z is the weight of the number of k-mers put inside, and W1 is XZ because W1 was this one. There is only width 1 and only one stuff. W2 is x to the power k, z to the power k. Sorry, W3 is x to the power k plus 1 because there is one extra. But now the horizontal stuff can be put in 2 ways. So it is 2 to the power k, 1 plus 2z to the power k. Okay, and then you write the condition for finding the density and determine the roots. And in the limit z goes to infinity, the equation is the same, and we recover the exact entropy of the full packing case with just 2 tiles. The third tile, what is the effect? Its effect is 2 to the power k z to the power k in the partition sum. Okay, 2 to the power k z to the power k x. But it takes into account the fact that for each removed z rod, there are 2 to the power k new configurations possible. So there is, once I remove a rod, there is a lot of freedom to reconfigure the existing rods, and we are taking care of this correction. The total weight of this term is 2 to the power kx, but x is k to the power minus k. And so I'm still safe. 2 to the power k divided by k to the power k is pretty small. So epsilon 2 is actually very small. It only comes because of this other third term. And the other 2 terms were full, these were holes. It doesn't change the leading behavior. It doesn't change the behavior of epsilon 1. It doesn't change the behavior of mu star determined by the tangent construction. We can include more tiles. So, in this construction, I can put W4. It's not a problem. You can do the calculation. Nothing changes because all these k to the power k is still there. It will kill everything that you are looking at. Okay. So just to indicate the kinds of changes you can make to this construction, now we will allow not strip of width k, but strip of width 2k. So you can have tiles which are looking like this. There is one tile which looks like this. Another, this is 1 by 2k. And this is k by 2k. There are only 2 tiles just now for simplicity. This 1 by k can be filled either with 2 tiles or with 1 sliding tile vertically. And this one can be filled fully or can be filled like this with again this same kind of freedom. Okay, and then you can calculate the weight W1, W2 and put the condition and then check. And HDD2 has higher entropy at full packing than HDD1, but the asymptotic behavior near K is unaffected. One can add more tiles as before, and it doesn't seem to change the behavior. Okay, so just as a final variation on this set of calculations, suppose you take a K stripe, then you can have some vertical parts. In between the vertical parts, everything is horizontal. So that is omega 1 to the power k, one-dimensional partition function raised to the power L, and then you sum over all of these and that gives you something. But unfortunately the length of this horizontal part can be very big, and so this calculation cannot be done analytically for arbitrary widths between stuff, but you can do it numerically. And numerically also it is pretty non-trivial to do because these things diverge pretty fast. Z is very big and L is very big, so numbers tend to blow up on your face. But anyway, you can actually solve this and you can get a figure looking like this. This is what I showed before. This is the density of holes as a function of mu. So this is a calculation on a K stripe. So this is, in the end, it's a one-dimensional calculation, and these jumps are not real jumps. If you zoom up this stuff, you will see that this is actually smooth for the finite K stripe. The claim is that when you go to the real infinity, they will actually become sharp. But with this calculation, you only see a result which is rounded off singularities. There is no real jump. Okay, so that one-dimensional stripe only shows rounded off singularities, but it suggests that there is a nearly first-order jump in the true two-dimensional problem, and that is the part we haven't shown. Okay, so the hard rod problem undergoes two-phase transitions as a function of activity Z of rods. For large K, the entropy per site at full packing goes like 1 into log K by K squared plus subleading terms. Conjectured asymptotically exact results for the first order nematic to HDD transition in the system of long rods. And the most interesting, So these are the results. The epsilon 1 has this behavior for large K, mu star has this behavior, epsilon 2 has behavior. And the interesting point is that all these are independent of dimension. So why does that happen? Well, can we understand that qualitatively? So one says that if you have density near full, then the best way to pack rods is to pack them in layers. Then the layers are independent of each other, and in each layer you see this happening. And so that is so in the end the behavior is dominated by the two-dimensional behavior. The other dimensions come freely along. And that's the explanation for this independence. There is a more general sort of meta theorem which says that the coefficients of logs are universal in statistical physics. And the argument is that log itself is scale invariant, of course. Coefficient of log is scale invariant because when you change stuff, the coefficient doesn't change. But here they are not actually, these stuff are not coefficients of log, they are multiplied by suitable powers of K. So it's a little bit non-trivial, but even so, I think if one were to formulate a suitable large-scale limit of this, some continuum theory, that continuum theory will have logs and it will have this behavior. And that we have tried to look at, but we haven't managed. And so let me stop here.
Thank you. We have some time for questions.
Cool talk. So I have a question. Is any of those techniques usable also to study L-shaped long rods?
We haven't tried. I think some of these techniques should be possible, but no, I don't know. I haven't thought enough about it. We thought a little bit, but we couldn't make much progress.
More questions? Yes, Sanjay.
I have a question about the non-lattice model. So in the lattice case in dimension D, you have D possible orientations for the rods. How is the non-lattice model defined? Do you impose the directions to be parallel to the axis, or you allow also?
So actually, this is a major difference between lattice models and non-lattice models. There, the orientational degree of freedom is continuous. So if you have rods which are nearly parallel, there is still some orientational degree of freedom, which is order 1 by k, which in entropy becomes log k, whatever. And those are more complicated, and they are harder to study using these techniques. However, in the end, if you take things like Hurd squares, k by k squares, and study their behavior, they are well approximated by lattice models. So I think in the end, everything conspires so that the large k limit is well behaved and well defined.
Okay, in the interest of time, maybe we should take questions for later. So let's thank the speaker again.
Okay.